All right, let's talk about something we see every single day: light. Specifically, we're diving into the amazing secrets behind mirrors and lenses. You know, these simple objects that can somehow bend, flip, and even focus reality itself. And they literally shape how we see our entire world.
Okay, so let's jump right in. You've definitely seen mirrors like this before, right? Maybe at a science museum or a funhouse. You know the ones. One makes you look super tall and skinny, the next one makes you short and wide, and another one flips you completely upside down. It's a good laugh, for sure. But it makes you think, why doesn't this mirror reflect reality? What is actually happening here?
Well, to figure that out, we don't need some high-tech lab. Believe it or not, the key to understanding all of this is probably sitting in your kitchen drawer right now. Yep, we're going to unlock the fundamental physics of reflection with a shiny spoon.
I'm serious. If you've got a shiny spoon handy, go ahead and grab it. If not, no worries. Just picture one in your mind's eye. Now think about it. What happens when you look at your reflection on both sides of that spoon? What do you really see? You're going to notice two totally different things. First, look into the inner part. You know, the scoopy part that holds the soup. Your reflection is completely flipped. It's upside down or inverted. But now, flip it over to the outer, bulging side. All of a sudden, your image is right side up, or erect. But it's also a lot smaller than your actual face, isn't it?
So that little spoon experiment? It actually demonstrates the two main types of curved, or spherical, mirrors perfectly. It's kind of cool, right? So let's take what we just learned in the kitchen and bring it into the world of science. Let's put some official names on what we just saw.
That inner side of the spoon, the part that curves inwards, that's what scientists call a concave mirror. And here's a super easy way to remember it. The surface goes in just like a cave. Concave. Simple as that.
Okay, so here's the most important thing to know about these mirrors. Concave mirrors are basically light collectors. Their whole job is to gather up light. Their inward curve makes any parallel rays of light bounce inwards, and it brings them all together at one single point. And this action, this is called convergence.
So what about the other side of the spoon? You know, the one that bulges out at you? Well, that is a convex mirror. Pretty straightforward, right? Its reflecting surface is curved outwards. And you see these things in action every single day. You know that little warning on your car's side view mirror? The one that says, objects in mirror are closer than they appear? Yep, that's because it's a convex mirror. It spreads the light out, which gives the driver a much wider view of the road behind them. The trade-off, of course, is that it makes everything look smaller, and because of that, farther away than it really is. So, okay, we've got two kinds of mirrors that seem to do the complete opposite thing. One gathers light, the other one scatters it. Now, you'd think they must follow totally different rules of physics, right? Well, here's the wild part. They don't. There's a single, super elegant set of laws that explains how light behaves with all mirrors. Flat, curved, it doesn't matter. Let's walk through this process step by step. Nice and easy. First up, you have the incident ray. That's just the beam of light that's coming in and hitting the mirror. Then, at the exact spot where that light hits, we imagine a line drawn straight out, at a perfect 90-degree angle from the mirror's surface. This imaginary line is called the normal, and it's super important. It's our main point of reference. And finally, you have the reflected ray. That's the light that bounces off.
Okay, so from those three pieces, we get our first unbreakable rule. It's called the first law of reflection, and it says the angle of incidence is always equal to the angle of reflection. To put it simply, the angle the light comes in at is the exact same angle it goes out at. Angle in equals angle out. That's the rule.
And the second law, it's just as simple. It basically says that the incoming ray, that normal line, and the outgoing ray all lie on the same flat surface, the same plane. Think of it like this. The whole thing could be drawn perfectly on a single sheet of paper. The light doesn't just bounce off in some random weird direction. It's a very neat, very orderly 2D event. And this is the big aha moment. This is where it all clicks. Think back to the spoon. On a concave mirror, because of that inward curve, that angle in equals angle out rule forces all the rays of light to bounce inwards, and they all meet at a single point. They converge. But on a convex mirror, that outward curve makes the exact same rule do the opposite. Every ray of light spreads out. They diverge. See, it's the same law, but the shape of the mirror completely changes the result.
All right, so we've pretty much cracked the code on reflection. But mirrors, they're only half the story. What happens when light doesn't bounce off something, but actually passes through it?
That's where we get into the world of lenses and how they bend light in a process called refraction.
And hey, just like with mirrors, there are two main types that are basically opposites. A convex lens is fat in the middle and it converges light. Sound familiar? It's a lot like a concave mirror. Then you have a concave lens, which is thicker at the edges and it diverges light, just like a convex mirror. So they bend light instead of bouncing it, but the outcomes are incredibly similar.
A classic example of a convex lens is a magnifying glass. When you hold it close to something, you get that bigger, right-side-up image. But here's the really cool part. As you move that object farther away from the lens, the image actually starts to shrink, and at a certain point, it flips completely upside down. A concave lens, though, is way more consistent. It's super predictable. It doesn't matter if the object is close or far away. The image you see through a concave lens is always going to be upright, and it's always going to be smaller than the real thing.
So, okay, this is all really cool science, but why should you care? What's the point? Well, the answer is pretty simple. These principles are literally everywhere. They are the engine behind so much of the technology that powers our modern world.
Remember how concave mirrors are amazing at gathering light? Well, that's what's inside a car headlight, taking light from a tiny bulb and blasting it out as a powerful, focused beam. Or how about when you're at the dentist and they use that little mirror to get a super clear, magnified view of your teeth? Yep, that's a little concave mirror. And then you have giant telescopes, using massive concave mirrors to collect the faintest whispers of light from stars millions of light years away.
And lenses? Oh man, they're even more common. The eyeglasses that help many of us see clearly, those are just precisely shaped lenses. Every incredible photo you snap with your phone, every microscopic world you explore with a microscope, every blockbuster movie you watch on a giant projector screen, none of it would be possible without complex systems of lenses, all working together to bend light just right.
And that brings us to one last, pretty mind-blowing thought. We've talked about everything from a kitchen spoon to giant space telescopes, some amazing pieces of technology. But the truth is, you are walking around with one of the most sophisticated optical devices ever created right in your own head. I'm talking about the human eye. It uses a flexible convex lens to focus the entire world onto your retina. So here's the question I want to leave you with. How does this incredible piece of natural technology, our eye, stack up against all the amazing optical tools that we build?